Welcome to our quantum deep dive. Today, we're getting into one of the most fundamental and honestly most elusive building blocks of our entire universe, the anti-up quark. And our guide for this journey is an absolutely fascinating essay from Jörg O. Schnepphat.
So we're going to start with what is, well, maybe the biggest question in all of physics. You see, according to our best theories, the birth of the universe should have been this perfectly symmetrical event. And in that perfection, it should have just vanished, leaving nothing behind but a sea of pure energy. So the real question is, why are we even here?
Right. The Big Bang should have created equal amounts of matter and its mirror image, antimatter. But here's the catch. When matter and antimatter get together, they annihilate each other in a flash of light. So a perfectly balanced creation would have led to a perfectly balanced destruction, leaving a cosmos totally empty of stars, planets, and us.
Okay, let's dive right into this. To figure out how our universe somehow survived this cosmic death pact, we need to follow this roadmap. We're going to start with the mystery itself, then we'll meet the ghost particle at the very heart of it, explore its really bizarre world, learn how we hunt for it, and finally get to why this tiny ghost matters for, well, everything.
So here's the crucial point. The very fact that we exist is proof of a cosmic crime, in a way. It tells us that the perfect symmetry between matter and antimatter was broken right from the very beginning. There was a tiny flaw in the mirror, an imperfection that literally saved everything.
And it's almost impossible to get your head around how slight this imbalance was. Just try to imagine it. For every billion pairs of particles that met and annihilated, there was one single leftover matter particle with no partner. That lonely survivor, repeated over and over across the entire cosmos, became the seed for every galaxy, every star, and every single atom in your body.
So, to get to the bottom of this life-saving imbalance, physicists have to dig into the universe's fundamental building blocks. And a key player in this whole antimatter family is a particle with a kind of curious name, the anti-up quark. You know, the name itself is a story. Anti comes from the Greek word for against, which makes sense. It signals its opposite nature. Up is just a label from way back, one of 6 quark flavors. It has nothing to do with direction. And quark, well, that wasn't pulled from some dry science textbook. The physicist Murray Gell-Mann famously borrowed it from James Joyce's novel Finnegan's Wake. It's this amazing blend of ancient language, modern physics, and even literary whimsy. And this table here really shows what anti means in particle physics. If you look, the mass and the spin are identical for both the up quark and the anti-up quark. They're twins in that sense. But the fundamental charges, like its electric charge, they're perfectly, completely inverted. It's a perfect mirror image in all the ways that really count for interactions. So the anti-up quark is the antiparticle to the up quark, which happens to be the lightest of all 6 quark flavors. This makes it incredibly important. Just like protons and neutrons, which are made of up and down quarks, form the nucleus of pretty much all the matter we see, their antimatter cousins are built from anti-up and anti-down quarks. It really is a fundamental ingredient of the simplest kinds of antimatter.
Okay, so we know what it is, but to understand how it behaves, we have to leave our familiar world behind and step into the truly bizarre realm of the strong nuclear force. It's governed by a theory with a very fittingly colorful name, quantum chromodynamics, or QCD.
So in QCD, quarks and antiquarks have this property called color charge. Now, this has absolutely nothing to do with the colors we see with our eyes. It's a quantum property, a kind of charge that runs the strong force. Quarks come in red, green, or blue, and antiquarks, like our anti-up quark, come in anti-red, anti-green, or anti-blue. The fundamental rule here is that any stable particle you find in nature has to be color neutral, or white, by combining these charges, kind of like a quark and an antiquark of a matching color and anticolor. And this leads to one of the absolute strangest rules in all of physics, confinement. See, unlike a magnet where the force gets weaker the farther apart you pull the poles, the strong force between quarks actually gets stronger. If you try to pull an anti-up quark away from its partner, the energy you have to pour into that bond becomes so huge that, thanks to Einstein's E equals mc squared, it's actually easier for that energy to just create a brand new quark and antiquark right out of the vacuum. So you end up with 2 pairs of particles instead of one free one. You can never, ever isolate an anti-up quark. It's a true ghost particle, forever locked up inside a larger system.
Which brings up a huge question, right? If we can never actually see an anti-up quark by itself, how do we even know it's real? Well, the answer is we can't observe it directly. So we have to create it and then watch very, very carefully for the footprints it leaves behind. The hunt for these ghost particles happens at these unbelievable places like the Large Hadron Collider at CERN. Inside this 27-kilometer ring, protons are revved up to 99.9999991% the speed of light and then smashed into each other. This creates these little fireballs of pure energy that, for a split second, look just like the very early universe. In the middle of that collision, pure energy turns into mass, creating pairs of quarks and antiquarks out of basically nothing. And among them are up and anti-up pairs. But sticking to that rule of confinement, the newborn anti-up quark only exists on its own for about 10 to the minus 24 seconds. I mean, it's an impossibly short amount of time. In that instant, it grabs a nearby quark and binds with it to form a new particle called a hadron, like a pion, for example. It's the pion that goes flying out into our detectors, and that's what our instruments actually see.
So, you see, the physicists are basically forensic detectives. They can't see the suspect, the anti-up quark, directly. What they do instead is meticulously record all the tracks and the energy of the secondary particles, all the evidence left at the scene. And by working backward, using the laws of conservation of energy and momentum, they can reconstruct what happened and prove, beyond a reasonable doubt, that the ghost was there.
This incredible forensic science brings us right back to where we started, to that original mystery. Why are we here? Because studying the tiny little differences in how particles like the up quark and antiparticles like the anti-up quark behave, well, that's the key to understanding the universe's life-saving asymmetry. Way back in the 1960s, a physicist named Andrei Sakharov figured out the recipe for a universe like ours. One of the key ingredients is that the laws of physics can't treat matter and antimatter as perfect mirror images. You can think of it like a left-handed glove and a right-handed glove behaving just a little bit differently. This subtle difference is called CP violation. And the experiments studying particles like the anti-up quark are exactly how we search for these tiny, universe-defining imperfections.
But this whole quest to understand the anti-up quark, it isn't just about answering these huge existential questions. This kind of fundamental research, pushing the absolute boundaries of what we know about reality's basic rules, that has always been the seed for future technological revolutions. And here's the direct connection to our future. The really complex math used to describe the anti-up quark, that quantum chromodynamic stuff, is just too hard for even our best supercomputers to handle. But it's a perfect problem for quantum computers. So by studying these particles, we're essentially writing the software for the next generation of computing. The bizarre rules they follow are also inspiring brand new ideas for things like unbreakable quantum cryptography and ridiculously precise scientific measurements. So that brings us to a final really provocative thought. The anti-up quark and this whole mystery of why there's so little of it, it teaches us something really profound. Our stable, matter-filled reality, it isn't the default. It's the unlikely outcome of a broken rule, a tiny flaw in the perfection of creation. It makes you wonder, doesn't it? What would a universe where that symmetry held perfectly even look like? Maybe just a silent, empty sea of energy. A reality that could have been, but wasn't. So in the end, the anti-up quark is so much more than just a particle. It's a clue to our own existence. It's a symbol of that subtle little imperfection that allowed everything we see to emerge from the void. We hope this deep dive, guided by the work of Jörg Oeschnapat, has helped shed some light on this ghostly but absolutely essential corner of our universe. To explore this topic more, you can visit schnapat.de. Thank you for joining us, and goodbye.
Schnapat.de is a private project by Jörg Oeschnapat dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.